So in this video, we're going to learn one application of matrices, which is to solve systems of equations. Matrices, especially if you have a calculator, can make solving systems of equations much quicker. And the bigger the system is, the more efficient the matrices method becomes. So let's start with an example that we've done before. We did this when we did the 3x3 systems of equations, and this is of course only 2x2, but I'm going to do it this time with matrices. So the first thing I'm going to do is I'm going to change the way this is written, and I'm going to write it using matrices. So it's going to look like this. The matrix 3, 2, 2, negative 5 times the column matrix xy equals the column matrix 11, 1. Now what I've done here is I've taken all of these coefficients, the 3, the 2, the 2, and the negative 5, and I made a coefficient matrix. And then I've taken the x and y and I made a column matrix out of it. And the reason I had to do a column matrix is so that this is a 2x2 and this is the 2x1. So the order, the dimensions in the middle are going to match. I couldn't do this as a row matrix. It had to be a column matrix. And also 3 times x plus 2 times y when I multiply together. That's that thing. And then 2 times x plus negative 5 times y. That's that thing. And then, of course, the answer here, this is called the constant matrix. So we have the coefficient matrix, the variable matrix, and the constant matrix. Now, in order to solve the system, I'm going to rename these now. For example, I could call this A times the matrix X equals the matrix B. So A is now the coefficient matrix, X is now the variable matrix, and B is now the constant matrix. And in order to solve, all I really need to do is to isolate the X matrix. If I can say X equals, then I've got the XY equals whatever the answer is. So I need to somehow figure out how to get rid of A. So remember, there's no such thing as dividing with matrices, but there is a way to get rid of the A if I can multiply by A inverse. So now remember, matrix multiplication has to be done in an appropriate order, and if I want the A to disappear, I need to make sure A inverse gets multiplied from the left-hand side. So it's going to be A inverse on the left here, and then A inverse on the left here, because I'm basically left multiplying by A inverse. So A inverse AX equals A inverse B. Now, of course, A inverse A is going to be identity. So this is identity times X equals A inverse times B. Well, identity times X is just X. So X equals A inverse times B. Now, because we're going to be relying on the calculator for a lot of the work here, I will want to see all of this work. Even though it's going to be literally identical, I want you to spit this out every single time to get full credit. That way I know that you understand that you've changed these the system into matrices, you've given them appropriate names, and you're multiplying from the left by the A inverse matrix, and of course that becomes identity, and so this is the final result. Now we're going to let the calculator do this work for us. However, we're going to report various steps along the way. So we start by creating matrix A, second matrix, go over to edit, select A, and then make the A matrix. It's a 2x2, put the answers in there, the numbers in there. Then second, quit to a blank screen. So now you're going to do second matrix, go over to edit, select B, and then make the B matrix, which is a 2x1 matrix. So put those in, and then second, quit to a blank screen. Now we need to know what A inverse is, and we're going to let the calculator do that for us. So we do second matrix, and under names we select A, and then it says A, and then we hit the X to the -1 or inverse button. We hit enter, and of course it gives me this ugly decimal, so we're going to fix that. So we go to the math button, select arrow fraction, hit enter. The screen says matrix A into a fraction, hit enter again, and then the screen gives us the answer, which we are going to write down in the context of the problem. So the X matrix is just XY. The A inverse matrix is the one we just found, which is 5/19, 2/19, 2/19, -3/19. And of course the B matrix is 11, 1. Now we're going to calculate what the A inverse matrix times the B matrix is. So as long as you haven't touched anything else on the calculator, the last thing you did was calculate this matrix over here. So this matrix should still be on your screen. So if you just hit the multiplication symbol, it'll take the answer, which was that matrix, times, and now whatever else you're doing. So second matrix, names, B matrix, enter. So now your screen should say answer times B matrix, and if you hit enter one more time, it should give you your answer. And this is one of those things, again, I would write down. So I've just figured out that xy equals, and then the product of these two matrices ended up being 3, 1. Now, if these were fractions or decimals, I would convert them to fractions, but they are nice whole numbers, so I don't have to worry about that. So finally, I need to report my answer, which is x equals 3, y equals 1. Now I've cleverly separated the work from the calculator stuff. The only thing I don't need you to write down in your solution is this. You don't need to give the names of the different matrices, but you do need to first convert the system of equations into one single matrix equation with the coefficient matrix, the variable matrix, and the constant matrix, and then literally write this down every time. This is A, this is X, this is B. You're going to multiply from the left side by A inverse on both sides. That'll turn into identity, which means you've just isolated X. And then copy from your calculator work what is the A inverse matrix, what is the B matrix, and then finally what is the answer you get from the calculator. So I want to see a couple things. I want to see your conversion. I want to see that you know that this rigmarole always applies. I want to see that you know how to find an inverse on a calculator and report it. And then I want to see that you know how to do multiplication on the calculator and report the answer that way. Otherwise, this could get very, very tedious in terms of showing a lot of work and finding the inverse and doing the multiplication, etc. So let's look at another example. So this is going to be a 3 by 3. This is the same 3 by 3 that I did earlier. And I'm going to do this and only show the work that I expect to see. I'm going to talk through what goes on the calculator, but I'm not going to write any of it down right now. So this is exactly the kind of thing I'm expecting to see on homework or on a test or something like that to show the appropriate amount of work. The first thing we're going to do is we're going to convert this from a system of equations into a matrix equation. So the coefficients are 2, 1, -3, 3, 2, 2, 1, 2, -1. So that's the coefficient matrix. The variable matrix now is x, y, z. It's a 3-row, 1-column matrix. And the constant matrix now is 17, 21, 14. Now I want to mention a couple things here. If these are in a different order, if it's not XYZ, 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 you need to rearrange them because this has to be the same order as over here. Also, if one of them is missing, so let's say this was just 2y minus z without the x, then you would put a 0 in the appropriate coefficient because there's still an x there, it just has a coefficient of 0. So the coefficient matrix has to have missing values listed as zeros. And the same thing over here, of course, but they would already be written down as zeros. So the first thing I did was I recopied the information into matrix form. And then I would say A times X equals B. Then I would say, well, I got to multiply from the left by A inverse. So A inverse times A times X equals A inverse times B. Again, this has to come from the left so that these are adjacent and they can turn into identity. And if I'm multiplying from the left on this side of the equal sign, I got to multiply from the left on the other side of the equal sign. So that's not optional. And then A inverse A turns into identity. So identity times X equals A inverse times B. And therefore X equals A inverse times B. And now I go to my calculator and I type all these matrices in and I do computations. So I start by typing this matrix into matrix A. It's a 3 by 3. I enter all of these values in there. I second quit to a blank screen. Then I type this matrix into matrix B. Again, it's a 3 by 1. I enter the numbers and I second quit into a blank screen. Then I go and I find A inverse by doing second names, A matrix, and then I hit the inverse button and then I hit enter and it gives me a whole bunch of decimals and I do arrow fraction to convert into a fraction. And then I start reporting this stuff to on the homework or whatever it might be. So on this time it's the screen. So the X matrix is just X, Y, Z. The A inverse matrix is now 6/19, 5/19, -8/19, -5/19, -1/19, 13/19, -4/19, 3/19, -1/19. That's what the calculator gave me. And then the B matrix is still 17, 21, 14. And I'll move over to the right here. So I'm reporting what the calculator told me was A inverse, and of course I'm recopying what B is. And then I let the calculator do this multiplication, so I just hit the times button. It'll take the previous answer, and then I multiply by the matrix B, and I end up with my final result, which is, of course, the XYZ matrix, still the column matrix, is equal to, and in this case they're whole numbers, so I'm happy, 5, 4, and -1, which was the result we got the first time around, and therefore x equals 5, y equals 4, and z equals -1. Now I am showing you the bare minimum acceptable work here. Anything less than this, anything missing from this, and you won't be getting full credit. So now the calculator is doing a whole lot of work for you, so I feel like I'm letting you get away with quite a bit. I never had you find the inverse. I never asked you to do the matrix multiplication by hand. So you're letting the calculator do a lot of the work for you, but this is the bare minimum work I need to see on the piece of paper to justify that you understand what's going on with this problem. And that's the end of that example. Let's switch gears for a bit. All right, so now I want to talk about the determinant of a 3x3 or any n by n matrix. So first I want to remind you that we did the determinant of a 2x2. So if this is the 2x2 and we want the determinant of that 2x2, it's A times D, that's from the main diagonal, minus B times C. A times D minus B times C. So now let's look at a 3x3 matrix, and it's a lot more complicated, but there's still a very nice pattern that makes it a little bit easier. So we've got this matrix, 3x3, and to get its determinant, here's what we do. We start with the top row, and we start, of course, with the A. So I'm going to write the A times, and now we create a new determinant. But to figure out what matrix goes in that determinant, we picked A. We throw out the DG and the BC because those were in the same row and column as the A that we started with. So throw out the same row and column, and that leaves you with EFHI. And that's the smaller matrix whose determinant we're going to use. So A times the determinant of, well, throw these two out because they matched up with the row and column of A. Whatever's left over is your new determinant. That's the first step. So I started with A, and then I created a new smaller matrix where the rows and columns that matched up with A disappeared. Now I do minus, just like I did over here, minus, Now I go over to the next term in this top row, which is a B. So I do B times, and again I create another determinant. Now, to figure out what matrix I need for that determinant, here's B. These numbers are in the same row, throw them out. These numbers in the same column, throw them out. So the numbers left over are D, F, G, I, and they have to keep their order. So D, F, Gi is the new matrix whose determinant I'm going to calculate, where all the numbers from the row and column that B was in, because that was the one we started with at the front here, got thrown away. Now we change signs again. So the first one was positive, and then it's negative. Now it's back to positive again. So plus C times another determinant. And again, to get the smaller matrix for that, here's my C. I throw everything in the same row and the same column as C. So I'm left with these four, which is D, E, G, H. So the determinant of D, E, G, H. So again, the general idea is to only use numbers from the top row, start with A, then go to B, then go to C, etc. And start with positive, then do negative, then do positive. If there was another one, we do negative again, another one positive, negative, positive, whatever. It keeps alternating positive, negative, positive, negative, positive, negative. Each time you start with the number, then you create a smaller matrix and you throw out everything in the same row and column as the number you're working with. So with the A, I threw out the B, C, and the DG and was left with a smaller matrix, which was EFHI, and I'm going to do the determinant of that one. Then, of course, I did the minus B, and then I threw out those two rows and columns, and I ended up with this matrix, and then plus C, and then I threw out those two rows and columns, left with this matrix, and so on. So, of course, that's the end of that because I finished the top row. So this would be a 3 by 3. Now, if this is a 4 by 4, I would just keep this pattern going. Now, we're not done yet because now we have to calculate this determinant, and this determinant, and this determinant. Well, that's not bad because we know how to do that. It's just a 2 by 2. It's just EI minus FH. DI minus FG, DH minus EG. So this is relatively straightforward. These are smaller determinants that we already know how to do. Now, if I'd started with a 4 by 4, when I do the throwing out of the row and column, I create new 3 by 3s. Each of those 3 by 3s, I got to do the exact same thing where I create a bunch of smaller 2 by 2s, etc., etc. So it does get tedious after a while, but luckily for you, I'm not going to ask you to do too many of these past, let's say, a 3 by 3. But this becomes a very useful thing moving forward, especially the determinant of a 3 by 3, and you're going to want to do it by hand. So let's do an example. All right, here is a determinant. Again, I use the absolute value looking symbols, meaning I want a determinant of this 3 by 3. So here we go. First, I'm going to start with the 1. 1 times a smaller determinant. Well, that smaller determinant is when I threw out the same row and column as the 1 is now the 5, 6, 8, 9. So determinant of 5, 6, 8, 9. Minus. Now I go to the 2. And now I multiply by a new determinant. Again, I throw away everything in the same row and the same column as the 2. So it's 4, 6, 7, 9. Determinant of 4, 6, 7, 9. And then this one was plus, this one was minus. Now it's back to plus again. Plus 3 times, and now I create another determinant. Now to get that determinant, I throw away everything in the same row and column as a 3. That's 4, 5, 7, 8. So 4, 5, 7, 8. All right, so now I need to calculate each of these individual smaller determinants. So here we go. 1 times, well, that's 5 times 9 minus 6 times 8. And then minus 2 times, well, that's 4 times 9 minus 6 times 7. And then plus 3 times, well, that's 4 times 8 minus 5 times 7. Now I'm going to do these individual calculations. So this is 1 times, well, that's 45 minus 48. Minus 2 times, well, that's 36 minus 42. Plus 3 times, well, that's 32 minus 35. Okay, so 45 minus 48 is negative 3, so this is 1 times negative 3. And then minus 2 times 36 minus 42 is negative 6. And then plus 3 times 32 minus 35, which is negative 3. And so this is really negative 3, and then minus 2 times 9, so plus 12, and then minus 9. So ultimately, this determinant is 0. So that's how you calculate the determinant of a 3 by 3 matrix. And that's the end of this video.